Welcome to Sportswear Wednesday, everybody. Remind me to fill in the Google form. I have to fill it in for yesterday and today. And today we're going to be looking at how to take sine waves or cosine waves and apply them to various situations that we'll find in the world. So one of the tricks that you can use when you are creating an equation or a function to model certain behavior in the world is start by sketching your graph. Can be really useful. Or even make a table of values rather than trying to dive straight into the equation. You can use your understanding of the situation to draw a graph and then look at your graph and say, how am I going to fit a curve that matches that? And then you can test what you create in Desmos and see if it matches the sketch that you made. So here is an example where Alexa is riding on a Ferris wheel. Her height above the ground in meters is modeled by h of t, where t is the time in seconds. So we have here 10 seconds, 20 seconds. So it looks like Alexa gets on the Ferris wheel over here. She starts going up. So she gets on at time 0. She starts going up, and at 10 seconds, she has risen 10 meters. She's risen from here to here. And then going up another 10 seconds, she reaches the top of the Ferris wheel right there. And then we'll come back down again, completing one period in 40 seconds. So we can look at this graph, and here's some of the information that we can get right away. So we know where's the midline of this graph. They've got it drawn on there for us.
Do we have this problem?
No, you're going to create your own. So this one is, this has the midline of 15. I could have put it on the back there. I have a blank page. Oh, whatever. 15 is our midline. The amplitude, well, we can measure that just visually because, again, we're not working with an equation yet, but we know she's going to go up to 25 meters in the air. And so there is our amplitude. That's a height 10. So our amplitude would be 10. And then what's the period here? Good. And so Dave can see that the period down here, we see going from 0 to 40, we see one full cycle. If she were to get on, like if somehow it had a raised platform and you got on the Ferris wheel there, went up, came down, and then rose back up here again, it might look more like a sine wave where it starts at the midpoint and then rises up and then goes down and rises up. Okay? But here we get on at the bottom point. If we were measuring a period from this point, we would want to compare that to that point there because we go up, come down, and go through one full cycle. Okay, so you just want to make sure you get one full cycle. Starting at the bottom, going to the top, and making it back down to the bottom again is a full cycle. Yeah, so we've got break real soon. We've got our Christmas break coming up real quick. And what we are in now is this situation where the finish line is in sight, and that's actually the time where you start running a little faster. Okay, and that means like focus up a little more and understand that you'll have time for these side conversations in the break. Okay, so here we just want to make sure we get through one full cycle, and that's how we would know that. So the period there is 40. And then our phase shift, would you like us to use sine or cosine to model this? Sine? Okay, I'll show you one for sine and one for cosine. Spoiler alert, cosine's simpler. And actually, I don't need any phase shift for cosine. I just use a little trick. But sine, let's take a look at sine.
I see.
So Siraj already knows what I'm talking about. Okay, here. This was our starting point for sine. Because if we take a look at the sine wave that we graphed yesterday, and you can just flip back to the front page of your the front page of your handouts. No, not this handout, Mr. Jennings. Graphing sinusoidals. This one, where you have your sine wave here. Sine starts in the middle, goes up, and then comes down, and then finally hits the bottom, and then finally comes back up to the middle. So, in this case, here is the starting point for sine. So we actually want to shift the whole curve towards that direction, so that this now becomes the starting position. So we're shifting it in the positive direction, and it's been shifted by how much? We just want to take a look at how much it's shifted here. So that's been shifted positively by 10. So that's how I can find my my phase shift, my D transformation. So if I move that over by 10, I'm moving it 10 in the positive direction. So I want what flavor of D when I write out this function? Yeah, negative 10. That's good. So I have f of x is equal to the amplitude. Let's get these on here. The amplitude there is 10 multiplied by sine. And then I'm going to put in brackets my k, which is my period. Well, what's the period? What do I need to use there? Well, what value will I use for the period? Suraj?
9.
9. How do you know? How does Suraj know? What wizardry does Suraj use to know that 9 is the correct answer here? 9 for k. Dave? 360 divided by 40. Remember that we have a formula to determine our k value, and that's 360 degrees divided by the period. So we want this to rise and fall and go through one complete cycle every 40 seconds. Normally it goes through every 360 degrees. So we need to have it do that 9 times in 360 degrees. So 9. 9, and then you have bracket x minus the phase shift, so minus 10, end bracket, end big bracket, and then we're going to add on the midline. We're going to say plus 15. Let's see if this function matches what we have in Desmos. Do I think you ought to be checking your work in Desmos regularly in this unit? Absolutely. It's a tricky unit. These things are slippery and funky, and you want to see as many examples as possible. Always make sure to move your face so that you can put it into degrees, and then come back here, and you know we want to see, and so then you're going to set your scale, and you're going to move your face to do that again. We want to see positive values of y up to like 25, so let's go 35 there. And then x-axis we want to see, we want to see 3 cycles, so go 120. And that should be good. That should show us enough info. Let's take a look now at what we've got. F of x equals, we had, what was it, 10 sine. Desmos doesn't like square brackets, so use a series of round brackets. 9 multiplied by another bracket, x minus 10, end bracket, plus 15. There. Let's see if we got the same function. So it goes up here to the maximum 20, 25, and then down to the minimum 4, 5. We can see the midline there right at that C value. So there's our C transformation, and it's describing the midline cutting right through the function there. The bottom of the function is there. The minimums are at 5, and the maximums are at 25. Let's see if I remembered all that correctly. Yeah, maximums at 25, minimums at 5. There is how we would move through this Ferris wheel. Now I said cosine would be simpler to use. Okay, let me sketch on what cosine would look like. Cosine starts at the top and goes down. It's going to intersect at that point, hit this bottom point there, and come up, and that would be one full cycle of cosine. So it might look like, well, I need to shift that over all the way that way. Okay, I need to use a D transformation of maybe positive 20 for my cosine. And that would work because this is the point, this is over here at 20. So if I add 20 to the inputs, it's going to shift that in the negative direction that way for cosine. But there's another trick I could use. What is it, Suraj?
It's having a negative a.
Yeah, let's just reflect it in the x-axis. So if we use a negative magnitude, it's going to flip everything in the x-axis, and then we could just use cosine with no phase shift. So let's try that and see if it matches over here. So it's going to have the same magnitude, except negative. So let's draw a g of x here. G of x is equal to, let's try negative 10. Cosine, let's start it without the negative. I'll flip the negative in a second. It's cosine of, it's going to have the same period, because cosine and sine have the same period. 9 multiplied by x, and I'm suggesting that we don't need any D transformation here to make this work. And it has the same axis. There we go. So notice that it's just a straight vertical translation of these things. If I, like a vertical, reflection. It's a reflection through the axis around C. If I make this negative, whoop, there it goes, right there. So I don't need any phase shift for cosine. I just need to have it be just my vanilla flavored cosine, and that will do it. But I also said we could still do it with this cosine. We would just need 9x minus 20 and bracket there. And x minus 20 would also do it. Because we had this point here that we pulled over that way to make it match. Okay? All right, so let's keep going. Now let's build our own Ferris wheel. You get to make your own Ferris wheel over here, okay? So here's what you can do. Draw a Ferris wheel there and apply some numbers to your Ferris wheel. I'm going to build one on the board. I might build one here. I might build one on the board. I kind of want to build one on the board. And then sketch what your graph is going to look like. Think of these not as degrees, but as seconds. So how fast is your Ferris wheel going to go to the top? How fast is it going to go to the bottom? You get to choose all these things. You can even choose where you get on the Ferris wheel, and are you rising or falling as you get on. Sketch your graph and then create your function. So, oh yeah, but before we do that, take a look at the anatomy of the Ferris wheel and notice the connection between the transformations of the sinusoidal function and the features of the Ferris wheel. What feature of the Ferris wheel determines how high the axis is? Brody, I'm about ready to pick you out. What features of the Ferris wheel determine the height of the axis? Yeah, the axle is the axis, right, Peter? Yeah, so the midpoint of the Ferris wheel, that axle where it's turning, is the equation of the axis. So its height over the Earth is your y value for that axis. How about the amplitude? What determines the amplitude here? The A transformation. Yeah, but what dimension of big the wheel is? The radius, right? So this radius r, this is also, you could also call this a. This is the amplitude of the Ferris wheel. And then the period, we don't see the period in the diagram. Unless you had an animation, you could show period. And that's connected to how fast it turns, right? You want to give you some head nods? Yeah. Sinusoidal motion here, periodic motion. Yes, yes, Mr. Dennings, I got you. Okay, and then the last one, phase shift. What determines phase shift here? D, yeah, D is our transformation variable that changes the phase of these functions. But what determines that in terms of this picture of the Ferris wheel? We don't really have it in this picture, but it's the idea of where we start, where we get on. This is the boarding platform. So in your diagrams, I encourage you to draw like a boarding platform there and say this is where people get on and they go in that direction. If we started them, say, like here, and had the boarding platform there, then that's where they would start and go around. But they could also start there and go down. More challenging Ferris wheel problems will have you boarding at like a certain angle away from the vertical or something. That's another way that you can put these problems together. So I'm going to pause the video. We're going to create some, you're going to use this space here to create your own picture of a Ferris wheel over here, and then create a sinusoidal graph for yourself over there. And I'm going to do that on the board because I want to. All right, so we're back from break, and we're going to take a look at some of these word problems here. So this is the task for today, or the word problems. Here's a water wheel problem. We're told that it's 14 meters in diameter, so that should give us some clues. Here, we'll go through the clues. Water wheel, this is going to be very similar to a Ferris wheel problem. It is a Ferris wheel problem. It's just a Ferris wheel for frogs. Oh, sorry, a Ferris wheel for a fish. Because a fish gets picked up at the bottom of the wheel, and it begins 2 meters below the water. So it's very similar to my situation. So if I were working on this, I would first sketch a picture. I would put the water on. I would draw a fish. Fish are drawn this way. They're like infinity, but you cut infinity in half on one side, and then you add an eye there. And then you see the water wheel, whee, and it goes underneath the water, and it comes up, and you draw a beautiful circle, which is not that. And then you know that it takes 6 seconds to get to the highest point. The fish is picked up 2 meters below, so this is 2 meters below. It's 14 meters in diameter, and that can all give you clues as to the midline. So we're not told where the axis is, but you have to calculate it. If this is 14 meters there, let me zoom in, I'll actually be able to write on here. If this is 14 meters here, then, do I have, yes I do. That's better. If this is 14 meters and this is 2 meters below the surface of the water here, this here is 2 meters. So that would be, the highest point would be at 26, because this is 28 in diameter and it's 2 meters below the surface. So the axis there would be, Dave? Yeah, it's 14 meters. What did I write? Something that no one can read. Sorry? Oh, it's 28. Oh, it's 14 meters in diameter. Yes, thank you. It's not 14 meters radius. So the radius is 7 here. Thank you very much. 7 meters. That would be something I would certainly take 1 mark off for if you did the rest of the problem that way. The midpoint is some unknown height, but if the radius is 7 meters and the lowest point is 2 meters below the water, what's the height of the axle here? 5, yeah. So we know that this, if the radius 7 went under the water by 2, that must mean that the axle is 5 meters above the surface. The formula is 7 minus 2. Very good. So we can find that. That gives us our C value there. Our A value is there. And so we've got C, we've got A. And then we have to develop our phase shift and our period. So let's do the phase shift and the period together, because A is very easy. So this will be something like f of x equals a sine x. So it's going to be 7 sine of something x plus or minus something. So I'm going to just put in our various brackets there. And then we're going to have plus 5. So let's figure that out. Our phase shift is going to come from its speed. So it goes 6 seconds and it's at the highest point. So how long does it take to complete 1 full revolution?
12 seconds.
12 seconds. So what value of k will produce a period of 12 seconds? How did you do that, Dave? You divide 360 by 12, and then you'll get the value of k that you want, which was 30, right? 30, yeah. So we want to multiply our x values by 30, and we need to phase shift this. So start again. You can start with your sketch as well. You can make a sketch. We know that it starts at the lowest point at minus 2. It goes up to the highest point in 6 seconds, and then goes down and was going to complete 1 period after 12 seconds. Okay? And then you're going to look at that and you're going to say, well, a sine wave normally starts right there. Normally starts at the axis. So I need to shift this whole function positively by however long it takes to go from the bottom to this midpoint. How much time would it take to go from the bottom to the midpoint there? 3 seconds. It's going to be half the time that it takes to get to the top. If I start at the bottom of my Ferris wheel, it's going to take me, well, my period here is 10 minutes. So to go from the bottom to the midpoint there, it's going to be 2.5 minutes. Then this is going to be the next 2.5 minutes. This is the next 2.5 minutes, and this is the next 2.5 minutes to get back to 1 full period. So that's something you can deduce in that way. So I know that if I do 7 sine 30x minus 3, all plus 5, that should do it. And then I go ahead and I check it in Desmos, because you do this kind of thing when you're doing this kind of unit, because it's really tricky otherwise. So I have, what was it? 7 sine bracket 30 bracket x minus 3 and bracket plus 5. Oh, there, that's really wrong, isn't it? What's my mistake? So I need to be in degrees. There we go. So now let's take a look and see if this works. Oh, look, the fish is getting on at the lowest point, which correctly is minus 2. And then the highest point over here is 12. That makes sense because the whole wheel is 14 wide, but it's 2 meters under the water. And then it completes a full period in 12 seconds there. Hooray, it works! So we did not make any mistakes. That is the correct function. Now you can use that function to solve other problems, like find 4 times where the frog is at the highest point. So there's 4 times. If you go in your DeLorean 6 seconds in the past, you'll find that the frog is at the highest point. If you go 30 seconds into the future by waiting, so you need far less technology to go that way in time, 30 seconds. It's going to be at the top again for the 4th time. Right? These are the ways you solve these problems. If you want to know, like, when is the frog at 8 feet high, then you could do this. You could say y equals 8 and find those points. Okay. The other way you could do it is you could say sine of blah, 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 blah equals 8, and then find all of those times where this x value would satisfy that. Finding that algebraically, it's not that bad. And you would use the unit circle to find all of the equivalent sine values. These would also be solutions to the problem, like a triangle. There's 2 possible triangles, and those would be those 2 triangles there for those values of sine. Do you have enough to get started on application problems? Go, and I will be visiting you all and seeing your work on these application problems. Dave. Okay. I'm gonna stop the video. Oh wait, I'll pause the video.